Hello, this will be a video for lesson 8.1. This is the last unit of the course, unit 5, and it's a quick one. There's only a few lessons to do. So the first one is an introduction to sequences. So you can see the two learning targets there. We need to be able to find the first several terms of a sequence that's been defined explicitly and recursively. And then we need to be able to evaluate a partial sum using sigma notation. Okay, so what is a sequence? A very basic definition is a sequence is just an infinite list of numbers arranged in a certain order. So for an example, got 5, 10, 15, 20, ... and it would continue on and on and on. This is an example of a sequence. Now there is some terminology that we need to be familiar with regarding sequences. Most importantly right now is the terms of a sequence. So right now you can see four numbers, the first four numbers written of this sequence. These are referred to as the first four terms. The 5 being the first term, the 10 being the second term, the 15 being the third term, 20 being the fourth term, and so on and so on. So those are called the terms of the sequence. Now, what spot number is in is important. That's why they're ordered. That's why they're called the first, second, third, and fourth term. Now, these terms can also be represented symbolically. And in our textbook, it's common to use the letter A. So the first term would be represented using A with a subscript of 1. So A sub 1. Second term, similarly, would be represented using the symbol A sub 2, and then A sub 3, A sub 4, so on and so on. The 10th term would be A sub 10. Now, just a general term or a random term from this sequence, not in any particular spot, would be referred to as A sub n, and this is what's known as the nth term. The nth term. Now it's typical for sequences to have a certain recognizable pattern. For example, I'm sure you've recognized the pattern in this sequence is just adding 5 every time. But what's more valuable is to recognize a connection between the spot that the number is in and then what the actual term of the sequence is. So the fourth term is 20, the third term is 15, the second term is 10. What we're doing then is taking the taking the spot that the term occupies and multiplying it by 5. For example, if it's in the fourth spot, 4 times 5 is 20. If it's in the third spot, 3 times 5 is 15. If it's in the second spot, 2 times 5 is 10. So the 10th spot, for example, 10 times 5 would be 50. So the 10th term would be 50. So what we do for the nth term is we try to figure out a formula to represent that nth term so that we could find any term of the sequence in any spot. And that's what's known as an explicit formula. So the explicit formula for this sequence is 5n, where n starts at 1 for the first term, and then equals 2 for the second term, 3 for the third term, and so on and so on. So the values of n, our inputs, are the positive whole numbers or counting numbers. So 1, 2, 3, 4, 5. Those values for n represent the spot that the term is in. And then once you multiply it by 5, you actually get the term of the sequence. So using this idea of an input value, which is n, and an output value, which is a sub n, we could think about this relationship as a function where we have a set of inputs and a set of outputs. So right now you can see I've written the sequence vertically in the output column, and then the input values I've written here, and those are just, remember, those represent where that term of the sequence is. N equals 1 represents the first term, n equals 2 represents the second term. So we can think about an explicit formula as an input-output relationship similar to a function. And so what we are going to be doing in our first objective here, or first learning target, is to use an explicit formula or an nth term to be able to generate the first several terms of a sequence here. And really all we're doing is plugging in n equals 1 for the first term, and then we plug in n equals 2 to find the second term, and so on and so on. And every sequence that we're going to look at here has its own unique explicit formula. So using an explicit formula to write the terms of a sequence looks like this. We're going to be given the nth term, or an explicit formula. Those two ideas are going to be used interchangeably. The explicit formula or the nth term, they mean the same thing. So given the nth term, we're going to write the first 5 terms of each of these sequences. The first one here, a sub n equals 3n plus 2. So this is the explicit formula. This formula can be used to generate any term of the sequence. For example, if I wanted the 12th term, I would just plug in n equals 12. But I just want the first 5 terms. So for the first term, I plug in n equals 1. If I plug in n equals 1, right here for n, I'm going to get 3 times 1, which is 3. 3 plus 2 is 5. So the first term is 5. Now to find the second term, I plug in n equals 2, plug it back into the same formula. 3 times 2 is 6, or sorry, yeah, 3 times 2 is 6, and then 6 plus 2 is 8. So the second term is 8. Now I want the third term, so I plug in n equals 3, and then use this same formula here. 3 times 3 is 9, 9 plus 2 is 11. And often you get to a point where you can recognize an easy pattern here. All that's happening is each term is being increased by 3. I'm adding 3 every time. So rather than continuing to input values of n, you can simply continue the pattern. The next term is going to be 14, the next term is going to be 17. So those are the first 5 terms of this sequence. We did start by using the explicit formula, but once you recognize that there is a pattern, you can just continue on with that pattern if you'd like. So try it here. Go ahead and pause the video and try to write the first 5 terms of this sequence. So as with the last example, the first term, you're going to use an n value of 1. So when n equals 1, plug it in here. 1 squared is 1. 1 plus 1 is 2. So the first term is 2. Now for the second term, I'm going to use a value for n of 2. N equals 2. Plug that in here. 2 squared is 4. 4 plus 1 is 5. Now for the third term, I'm going to plug it in here. 3 squared now is 9. 9 plus 1 is 10. So we're not adding 3 every time here. So looks like we added 3, then we added 5. For n equals 4, plug a 4 in here for n. 4 squared is 16. 16 plus 1 is 17. So it looks like the pattern is here I added 3, then I had to add 5, then I had to add 7. So it would make sense that for the next term here, you'd be adding 9. But just to verify, let's see, when n equals 5, because I want the 5th term now, 5 squared is 25 plus 1 is 26. So we did add 9. So there's the first 5 terms there. Let's go ahead and give you one more practice problem here. Go ahead and pause the video, try this one. Try to write the first 5 terms of this sequence. Okay, so we have 2 places now that we have to use an input. We're going to plug in the same value for n here and here. So as we have done with the last ones, we're going to start with a value of n equals 1 to find the first term. So -1, in the numerator, we're going to have -1 to the first power, which is -1. And then we're going to divide that by 1. -1 divided by 1 is -1. Okay, for the second term, we're going to use a value of n of 2. So then that's -1 squared, which is 1. And then 1 divided by 2 is 1/2. So the second term is 1/2. Now for the third term, we're going to use an n value of 3. -1 to the third power is -1. And then -1 divided by 3 is -1/3. For the fourth term, we would use an n value of 4. -1 to the fourth power is 1, +1. And then 1 divided by 4 is 1/4. So you can see a pattern emerging here that every odd term is negative. Every even term is positive. So since I'm looking at the 5th term here, I know it's going to be negative, and it's just going to have a denominator equal to its n value. So that's what it means to use an explicit formula to write the first several terms of a sequence. One advantage of an explicit formula or an nth term is, excuse me, you don't necessarily have to go in order. For example, what I mean is if I want the 20th term, I don't have to write the first 19 terms to find the 20th term. I can just plug in n equals 20, and then I get the 20th term. Or if I want the 100th term, I can just plug in 100 into the explicit formula, and I get the 100th term. So that's an advantage of using an explicit formula or an nth term. You can find any random term at any spot simply by plugging in its n value. Now, there is another way to represent a sequence, and it's called the recursive formula. So now this is the next part. This is part of the same learning target. It's our first learning target, where the first learning target was to use either an explicit formula or a recursive formula to write the first several terms. So now we're going to look at a recursive formula. So you see here that I've got another sequence written. And by the way, sequences don't necessarily have to have values that are increasing, where we're adding a number every time. They could also be decreasing. And so this could have started at 9 and gone 6 and then 3 and then 0 and -3. So just so you're aware, they're not always represented by increasing values. But anyway, I've got a sequence here. And I'm sure you've recognized that all I'm doing in the sequence is adding 3 every time. So the next term here would be 21, and then 24, then 27. I want to go back to this notion of just any term in the sequence, not in any particular spot, but just for the sake of argument, I'm going to say, all right, this is just a general term, a sub n, right here. I know it's the 4th spot, but I'm just going to call it a sub n for the sake of argument right now. The next term in that sequence can be represented by just increasing the value of n by 1. So if I'm talking about this particular term and I'm calling it a sub n, then the term right after it, I would have to add 1 to its n value because it's the very next term. So I would call it a sub n plus 1. what that means is the term after this one, okay? And then the next term would be represented as a sub n plus 2, and that's all based off of this particular term right here. So if I say, all right, I'm choosing this term to focus on, a sub n, then this term is a sub n plus 1, this is a sub n plus 2, because it's two terms after that one. The one in front of it, this one, in this case, has an n value that's 1 less than this n value, so it can be referred to as a sub n minus 1. And then the term in front of that one could be referred to as a sub n minus 2, and that's all in reference to this term that I've chosen here, a sub n. Where I'm going with this is recursive formulas commonly use this kind of idea. So, for example, the first term I could say, we know in this sequence is 3. Now, if I want to refer to this term right here, now forget about it being the fourth term or even that it's 12. Just say, okay, that particular term right there or any term in that sequence a sub n, don't think about the explicit formula. The explicit formula here would just be 3n. A recursive formula refers to a previous term. So what's the relationship between this nth term right here and the previous term? A recursive formula always refers to a previous term. So if we're looking at the relationship between this term and the term previous, the relationship is adding 3. And that's true of any term. If I call this the nth term here, 18, what's the relationship between that nth term and the term previous? And the relationship is we're adding 3. So the way we would represent this is the nth term is equal to the term right in front of it, a sub n minus 1, and then you add 3. And this is a recursive formula right here. A recursive formula has two parts. It'll always tell you where to start with the first term, and then it tells you how to get the next term, and the next term is found by taking the previous term and adding 3 to it. So an example of how you would use this. I know we already know what the sequence is, but let's just use this recursive formula to generate the exact same sequence. So according to this statement here, the first term is 3. Now what I need to get is the second term here, or the next term. So according to this, the next term is the previous term, and then you add 3 to it. So if I want the next term here, what I need to do is refer back to the previous term and add 3. So previous term plus 3 gives me 6. Now I need the next term after that. So I go back to this same recursive formula. All right, the next term, a sub n, the next term is I have to refer back to the previous term in front of that one, and then I add 3. So if I want this term, I have to go back to the previous term, which is 6, and add 3, then I get 9. So let me get rid of that circle there. So now I have 9. Okay. Now the next term refers back to the previous term and then add 3. So I get 12. And then the next term, I have to refer back to the previous term and add 3, and I get 15. So essentially we're just adding 3 in succession. So then I get 18, then 21, then 24. So a recursive formula is useful to quickly generate terms in order, starting with the first term. What you cannot do with the recursive formula is pick a random term, say, all right, I want the 50th term, because in order to get the 50th term, you have to know what the 49th term is and add or multiply a certain value to it. But in order to get the 49th term, you also would have to have the 48th term and then the 47th. So you can't skip around in a recursive formula. You have to go in order, starting with the first term. And then you have to use this recursive formula to know what to do next after the first term. So as an example, given these recursive formulas, write the first 5 terms of the sequence. So it tells us right off the bat the first term, and recursive formulas will always start by telling you at least the first term. Sometimes it tells you the first and second term, but we know the first term is 1, so we're part of the way there. We know the first term of the first 5 terms that we need to know. And now we use this part of the recursive formula to find the next terms. So the a sub n in this case can be thought of as the next term. So I need the next term. What it tells you to do is refer to the term right in front of it. A sub n minus 1 is the term in front of this one. So to find the next term, you use the term in front of it and you add 4. So to find this term here, I have to refer to the term in front of it and add 4, and that's going to give me 5. Now, to find the next term, I keep doing the same exact thing. To find this term, I have to refer to the term in front of it and add 4. I'm always adding 4. According to this formula, it says add 4 every time. So if I add 4 to the term in front of that one, I get 9. Now I need the next term here, and according to this, the next term, you take the previous term, add 4. So to get this term, I have to use the previous term, add 4, you get 13. So as you can see, we are just adding 4 every time. And I know I've written more than the first 5 terms, but you get the idea. A recursive formula just tells you a pattern that you, or a mathematical operation that you perform on each previous term to get the next term. In this case, we're adding 4. So let's practice it again. Part B. Go ahead and pause the video. You guys try this one. Alright, so again, recursive formulas will always start by at least telling the first term. So we have the first term there, which is 4. And then according to this now, the next term, which is a sub n, the next term here, we're going to take the previous term and just multiply it by 2 every time. So now the mathematical operation is just multiplying by 2. So the next term here is the previous term multiplied by 2. So that would be 8. And then the next term would be the previous term here now multiplied by 2, which is 16. And then the next term would be the previous term now, which is 16. So that's going to be multiplied by 2, which is 32. And then the previous term multiplied by 2 would be 64. And so on and so on. So those are the first 5 terms. And here's a little more of an unusual one. So part C, we've been given the first 2 terms. The first term is 3, the second term is 5. So 3 and then 5. So now I know the first 2 terms. Now the next term here, a sub n, you got to look closely at this and listen carefully. The next term says that you add the term in front of that one plus the term in front of that term. So if this is a sub n, the term I'm looking for, then the term in front of that one is a sub n minus 1, and the term in front of that one is a sub n minus 2. So according to this formula, this term here is equal to the sum of these 2 terms, a sub n plus 1, or n sub n minus 1 plus a sub n minus 2. So you have to add the 2 terms in front of it. So the next term, the term I'm looking for right now, would be the sum of the two terms in front of it. So 3 plus 5 is 8. Now the next term would be the sum of the two terms in front of that one. 8 plus 5 is 13. Now this term would be the sum of the two terms in front of that one. 8 plus 13 is 21. This is how the Fibonacci sequence works, if you're familiar with that term, and I think they introduce it at some point in the homework, but the Fibonacci sequence acts this way, where you're adding two terms prior to get the next term. So that finishes up the first learning target, using either an explicit formula to generate terms of a sequence or a recursive formula to generate terms of a sequence. Now, the last learning target is a partial sum, the idea of a partial sum. And other textbooks refer to this as a series. We're going to continue to call it a partial sum just to stay congruent with our textbook's notation or terminology. But a sum of a sequence is just adding terms of a sequence together. Now, because a sequence is an infinite list of numbers, we're not going to obviously add all the terms together. We're going to consider the notion of a partial sum, meaning, all right, we're going to add the first 10 terms of a sequence together, or the first 100 terms of a sequence together. That's called a partial sum because we're only taking a portion of the sequence and adding it together. That can be considered what's called a series. When you add terms of a sequence together, you start getting a series. So to illustrate, I've got 2, 4, 6, 8, 10. That's just a sequence where we're adding 2 every time. The explicit formula would be 2n. So partial sums work this way. If I want, and we're going to use now S to denote sum, and the subscript means how many terms of the sequence we're adding together. So the sum of just the first term is what this means right here, the sum of just the first term. Obviously the first term is 2, so its sum is just 2. If I want the sum of the first 2 terms, that's what this symbol means, the sum of the first 2 terms, so that would be 2 plus 4, so that partial sum would be 6. If I wanted the sum of the first 3 terms, you can see it's 2 plus 4 plus 6, and so on and so on. The sum of the first 4 terms would be 2 plus 4 plus 6 plus 8, which would be 20. So this is a less common way of notating partial sums, using this symbol S with a subscript. And the drawback or the limitation of this notation is it has to be starting with the first term. So for example, S sub 10 means you take the first 10 terms of a sequence and add them together, which doesn't seem like a drawback, but this notation is limited in this regard. If I didn't want to start with the first term, if I say wanted to start with the 10th term and say, all right, I want you to add the terms of the sequence starting with the 10th term up to the 19th term. This notation we wouldn't be able to notate that with this notation starting in the middle of a sequence, for example. And so a more common way of denoting partial sums is what's known as sigma notation. Sigma is a letter in the Greek alphabet. So I'm going to introduce sigma notation to you by looking at this problem here. I want to find the sum of the first 6 terms of a sequence with an explicit formula of 3n plus 2. So first of all, the first 6 terms of the sequence, we don't know what those first 6 terms are, but we do know an explicit formula, so I can write the first 6 terms using this formula. The first term would be n equals 1. So then 3 times 1 is 3, 3 plus 2 is 5, so the first term is 5. Second term would be 3 times 2, because n equals 2 now. 3 times 2 is 6. 6 plus 2 is 8. And the third term would be 3 times 3, which is 9. 9 plus 2 is 11. And then you can see that we're just adding 3 every time. So 14, 17, and then 20. So these are the first 6 terms of the sequence, and the sum would be just adding them up. Now this is not sigma notation. I'm just showing you what those first 6 terms of the sequence would be. But here's sigma notation. Here's how you would represent this whole statement. You can represent this entire statement using one single symbol. So sigma, like I said, is a letter in the Greek alphabet. It kind of looks like that. So first of all, this symbol right here, when you see this symbol, it denotes partial sums of a sequence. So when you see that, you need to think, all right, I'm adding a certain number of terms of a sequence together. Now the bottom here is the beginning value of n, and since it says the first 6 terms, then I know that n is going to start with a value of 1 and n is going to end with a value of 6. So you put the ending value of n at the top and you put the beginning value of n at the bottom. So this tells me I'm going to be adding from the first 6 terms of the sequence. And then here on the right side of sigma is where you write the explicit formula, 3n plus 2. Right here. So this symbol right here says the exact same thing as that statement. The symbol sigma itself denotes find the sum, and then the combination of these two numbers here means find the first 6 terms, the sum of the first 6 terms, and then those 6 terms are going to be given by that formula right there. So sigma notation is useful in shortening up a mathematical statement into a symbol. But it also means that you don't necessarily have to find terms starting, or the sum of terms starting at the beginning. I could have said, all right, start with n equals 7 and end with n equals 20. What this means is find the sum of the terms of the sequence from 7 to 20. So you don't have to start at the beginning. But going back to where we were, starting with the first 6 terms, n equals 1 to n equals 6, you do have to use the explicit formula to actually write down what those terms are so that you can add them together. So 5 plus 8 plus 11 plus 14 plus 17 plus 20 would be the sum of the first 6 terms of that sequence defined by 3n plus 2. So this is what sigma notation is. So now we're going to use it. I'm going to do some examples. And rather than having a mathematical statement written out, it's going to be represented symbolically. And, oops, let's use, there we go. The textbook does, I suppose, to spice things up, vary its variables. It doesn't always have to use n. The important thing is whatever variable is used here, it has to be the same variable used there. So it doesn't always have to be n, it could be k. All that means is the explicit formula is going to be defined in terms of k rather than in terms of n. So what this symbol means is to find the sum, and I know it's a sum because we have sigma there. Find the sum of the first 4 terms, and I know it's the first 4 terms because it has to start with k equals 1 and it ends with k equals 4. So those are the first 4 terms of the sequence defined by the formula 2 times k. So now that we know what to do, we actually have to write down those first 4 terms and add them together. So the first term would be when k equals 1. If you plug it in here, 2 times 1 is 2, so the first term is 2. The next term would be when k equals 2. You plug that in here, 2 times 2 is 4. And rather than just listing the terms, because we're adding this together, I'm just going to add them there. The next term is when k equals 3. So 2 times 3 is 6. And then finally we end when k has a value of 4. So k equals 4, that would be the fourth term. 2 times 4 is 8. 2 plus 4 is 6. 6 plus 6 is 12. 12 plus 8 is 20. So the sum of the first four terms of this formula, 2k, is equal to 20. All right, let's have you try one on your own. So I'm going to go ahead and say, all right, let's go back to n, starting with n equals 1 to 5. Find the sum of the first 5 terms of this sequence, n squared plus 2. So go ahead and pause it now, try to find the sum of the first 5 terms of that sequence. Okay, so in order to add the first 5 terms of the sequence, we need to know what those first 5 terms are. So when n equals 1, that's the first term, we're going to plug in a 1 right here. 1 squared is 1, 1 plus 2 is 3, so the first term is 3. Now, I'm going to add that to the second term. The second term is when n equals 2. And you don't need to write these here. I'm just trying to help you see the correlation between the value of k in that case or the value of n. So n equals 2, plug that in here. 2 squared is 4. 4 plus 2 is 6. Now the third term is when n equals 3. So if I plug a 3 here, 3 squared, 9. 9 plus 2 is 11. Now the fourth term is when n equals 4. 4 squared is 16. 16 plus 2 is 18. And then finally the fifth term, and I know I'm going to stop there because it says go from n equals 1 to n equals 5. The fifth term would be n equals 5, so plug in a 5 there, and we get 5 squared is 25. 25 plus 2 is 27. So now I need to find the sum of those 5 numbers. So let's see, 3 plus 6 is 9, and then 9 plus 11 is 20. 20 plus 18 is 38, and then 38 plus 27, let's see, 38 plus 27 is 65. So the sum of the first 5 terms of that sequence would be 65. So that finishes up that last learning target. So just to wrap everything up, in this section you've learned how to write the first several terms of a sequence using either an explicit formula here or a recursive formula, which refers to a previous term. And we've also learned how to find partial sums, most importantly using sigma notation to find a partial sum of a sequence.